in this lecture, we'll see how a module can be written as a sum of indecomposables. So the main theorem is the following. Suppose M is an R module that satisfies the descending chain condition. Then M can be expressed as M1 plus Mk, where each Mi is indecomposable for I between 1 and k. Now, before I give you the proof, let me just give you the proof idea. So the proof idea is the following. You start with M, and then, well, if it's indecomposable, then you're done. Okay, if it's not indecomposable, then you can break it up as a sum of two submodules, both of which are non-trivial, say M1 and M2. Now, if M1 and M2 are both indecomposable, then you're done. Otherwise, it's possible that otherwise one of them is not indecomposable. So let's say M2 is not indecomposable. So if M2 is not indecomposable, then I can further decompose it into M21 and M22. And let's just for the moment assume that M1 is indecomposable, so I won't do anything to it. Now again, if M21 and M22 are indecomposable, then what we have is, now note, we have M is M1 plus M2, but M2 is M21 plus M22, and well, you need to prove a certain associativity property of direct sum decompositions, which says that you can remove these brackets. But it turns out that M is now a direct sum of M1, M21 and M22. And now if these two were M21 and M22 were both indecomposable, we would be done. We would have a direct sum decomposition of M into indecomposable modules. But maybe they are not. So in that case, what we would do is we would go M212, M211, M212, M221, M222, and then again continue this until the process must either this process goes on indefinitely or it must stop after finitely many steps. We'll see that the descending chain condition will ensure that this process stops after finitely many steps. Now at each step there are certain modules, these ones, which are not branched yet. So either they are indecomposable or at the next step they'll get branched. So these ones circled in green are called the leaves of the binary tree at that stage. Okay, so this if we can show that this process will stop, then we'll have an algorithm to write M as a sum of indecomposables. So this whole thing is called a tree. It's called a binary tree, and these nodes which don't have any branches, these are called leaves. Okay, so now let's just write down this algorithm a little more formally. So here's the algorithm. And we'll show that this algorithm stops by using the descending chain condition. So start with T equals just one node, the tree, with one node M. Okay, so at the first stage, your tree has just this one node M, which is a leaf. Now, the algorithm goes as follows. If every leaf of T is indecomposable, T is the direct sum, M is the direct sum of the submodules corresponding to the leaves. And then you stop. You stop with direct sum decomposition into indecomposables. Else, for every leaf M star that is not indecomposable, add branches. M star below M star, which is namely M star 1, M star 2, where M star 1 and M star 2 give a direct sum decomposition of M star. Okay, so this algorithm just runs, and my claim is that this algorithm stops after finitely many steps. Well, if not, what will happen? So if not, there exists a path, an infinite path along the tree, consisting of nodes M containing properly Mi1, so it would be either M1 or M2, which properly contains Mi1, I2, which properly contains Mi1, I2, I3, and so on, where I1, I2, I3 all belong to the set 1, 2. And this would be a strictly decreasing chain of submodules which would not stabilize, contradicting the TCC. And so every module that satisfies the DCC can be written as a direct sum of indecomposable submodules. So this algorithm proves the claim. Let's look at an example. So let's take M to be Z to the power N, which is nothing but the set of all functions from the natural numbers to integers, and we think of it as a Z module. Addition is just a pointwise addition of functions, and multiplication of a function by an integer is also just multiplication of its values. So now for any S subset of n natural numbers, define Z to the S to be those functions f from natural numbers to Z such that support of f is contained in S. That means f is 0 unless f of n is 0 unless n belongs to S. Then for any S, okay, so then what we can do is we can draw the following tree. So let's just run the algorithm. So M, well, M is not indecomposable because I can write it as a Z direct sum Z subscript 2, 3, 4. This is the value of this decomposition. I'll just think of this as functions which are supported only at 1. And these are the functions that are supported at 2, 3, 4, and so on. And then this can be written as z direct sum z 3, 4, 5, and so on. And then this again can be decomposed z 4, 5, 6. So what this example illustrates is that when this algorithm runs forever without stopping, then here you see along this branch of the tree we get a descending chain of submodules that never stabilizes. So the chain z to the n contains z to the 2, 3, 4, contains z to the 3, 4, 5. This violates the DCC.